In this short video, we're just going to illustrate an example in which we see that derivative and antiderivative relationships that we know exist between functions are still true between their Taylor series representations. So for example, if we have a function f of x is equal to sine of x, we know that the derivative of sine is equal to cosine. And we're just going to illustrate that this is an example in which we're going to be able to see that the Taylor series also illustrate the same differential relationship. So for example, if we take sine of x, we could rewrite sine of x in its Taylor series centered at 0 or its Maclaurin series form from the series of series from n equals 0 to infinity of minus 1 to the n, x to the 2n plus 1 power all over 2n plus 1 factorial. And what we're going to do is just differentiate both sides. And we're going to illustrate that this relationship still holds. Of course, this is just an example, but hopefully this example sort of convinces you or builds some intuition that this is going to be true. So if we differentiate sine, we of course get cosine. And what we're hoping to see is when we differentiate that right-hand side series, we're going to get the Maclaurin series for cosine. So let's see if that happens. Well, the next step is we're going to pass this derivative inside our series and basically ask, what terms is this derivative operator actually going to affect? And well, since it's a derivative with respect to x, it's only really going to affect the terms that have x's on them. So it's going to pass right by this minus 1 to the n. It's going to pass by the 2n plus 1 factorial in the denominator, since those terms have no x's. And then we're just left with the x to the 2n plus 1 that is going to get hit by that derivative operator. So now let's take that derivative. And since this is x raised to some power, we can do the derivative or differentiation power rule. And we're just going to bring down that 2n plus 1 after we differentiate. And then we're going to subtract 1 off of that power, so we get x then just to the 2n power, just by the derivative power rule. And we're just going to be able to do a little bit of algebra to see this is actually going to clean up to the cosine series. So for example, we have this factor of 2n plus 1 factorial, and we see this lonely factor of just 2n plus 1. Using factorial algebra, we can rewrite this 2n plus 1 factorial as 2n plus 1 times a 2n factorial. And then we're going to be able to see that that 2n plus 1 factor is going to cancel out that 2n plus 1 factor now in the denominator. So let's rewrite this resulting series. So the series we're left with is minus 1 to the n. We have x to the 2n. And in the denominator, we just have that 2n factorial. And of course, we can recognize this to be the cosine Taylor series centered at 0 or the Maclaurin series. So again, in this case, we're just illustrating that the same differentiation and anti-differentiation relationships that we know to exist between functions are still going to be true in their Taylor series or Maclaurin series representations. This isn't a proof, but hopefully this builds a little intuition that this is indeed true.